In this question, actually, they are saying compound X is a single pure optical isomer, and compound X is heated with an excess of concentrated sulfuric acid. So that means elimination reaction, removal of water from, we can see alcohols, they are. So they are saying only one organic product is formed. So if we look at this option A here, we can see there is carbon with which OH group is attached. So it can show elimination by losing either water from this position, or it can also show the elimination of water. So what we can get, we will get double bond here, or another possibility, the double bond here. So different positions according to these substituents which are present on this ring. So they will give us different positions. So two different compounds are possible. One at the double bond at this position, and the another one having a double bond at the adjacent position. So two different compounds are possible in A. They are saying only one organic product. Okay. In this case, here carbon is bonded with OH group, and let's see the possibilities. It can show elimination by losing water. So we'll get double bond here. Is there any other possibility? This carbon is bonded with hydrogen as well. So let me show in different color. That can also show elimination of water. So we can get double bond here. So two different positions of double bonds indicates two different compounds. So not this one as well. Let's see option C. Here, carbon is bonded with OH group, and that is CH3. So again, different possibilities are there, isn't it? It can lose either show elimination by this or with this adjacent carbon. So here double bond is possible, here double bond is possible, here is also possible. So that indicates three different compounds are possible. Okay, but here in this case, you can see only one product is possible, which is the elimination of this water, and we get double bond here. So that is the only product which is possible in this case, right? So option D is correct. They are saying the only one product which is possible. Is it clear? In this case, they are saying which reagents could be used to form 2-bromobutane. The position of bromine is at second from butane 1-ol, and the OH group is, so we can think about it whether it could be substitution reaction, but here in this case the positions of the both the groups, they are different. In option A, they are saying bromine and ultraviolet light. So remember, that is a free radical substitution reaction. Alkanes can undergo these free radical substitution reaction in presence of ultraviolet light. So the bromine can be at any position here on the carbon atoms. The bromine can substitute the hydrogen atoms, but OH group will be there. So here we are going to prepare 2-bromobutane. We have to remove the OH group. So that's why option A is not Correct, right? Secondly, they are saying concentrated sulfuric acid with potassium bromide under reflux. So we know that when we react sulfuric acid with potassium bromide, so what actually happens? Sulfuric acid gives potassium sulfate and HBr should be produced, but we know that it's is in excess. So that will further convert this bromide, which is negatively charged, so that oxidize it into Br2. So bromine will produce here along with in the form of brown vapors. So bromine cannot, Br2 cannot substitute this OH group, but as we know, OH is already on carbon 1, but we are going to produce the product in which the Br is on carbon 2. So not option B. Let's see option C, concentrated sulfuric acid and then followed by bromine. Okay, if we use concentrated sulfuric acid, so what happens? Elimination reaction and we will get one butene, right? And when we treat it with the bromine, so what happens? We get addition reaction. So 1,2-dibromobutane will produce. So option C is not correct. Now next, same concentrated sulfuric acid. So elimination reaction will take place and we will get one butene. And now if we treat it with HBr, remember what's the rule? When unsymmetrical reagent like this with partial positive, partial negative is added on unsymmetrical alkene like this, in which you can see the two halves are not same. This negative part goes to the carbon which is making double bond and having less number of hydrogen atoms. This one has two hydrogen atoms, this one having one hydrogen atom. So Br goes to the second carbon and our product will be 2-bromobutane. So addition of unsymmetrical reagent to unsymmetrical alkene. So the negative part of the reagent goes to the carbon having less number of hydrogen atom, which is also known as Markovnikov's rule. So remember, we also discussed about the stability of this secondary carbocation, which is produced in these type of reactions. So option D is correct because we are going to prepare this 2-bromobutane. In this question, they are saying X is organic compound containing carbon, hydrogen, and oxygen only. And the table shows observations made from three chemical tests carried out. So first one is sodium solid is added. As we know, sodium is very reactive metal, and sodium can react with the alcohols. For example, I take this alcohol. So that can displace hydrogen from an alcohol. So it will give us uh, sodium alkanoate and sorry, not alkanoate, sodium alk oxide along with the hydrogen gas. So effervescence will be produced in this case. And sodium is also very reactive that can react with alkanoic acids and it can produce alkanoate ions, right? And hydrogen gas will produce. So effervescence will be seen if sodium comes in contact with an alcohol or carboxylic acids. So let's see option A. Option A has both carboxyl group and alcohol. Remember, this one is secondary alcohol. Option B has alcoholic group and an aldehyde here. So that can also show effervescence. It is again secondary. Option C has an aldehyde, right? And here it's tertiary alcohol. So option C, B, and A, all these three will show effervescence with sodium. Option D has carboxylic acid as well as tertiary alcohol. Okay. So all four options, they are showing effervescence with the sodium. Okay. Next, they are saying sodium carbonate. We know that sodium carbonate acids, they can react with sodium carbonate and produces salt and carbon dioxide plus water. So in these options, A has a carboxylic acid group. It will show effervescence with this. B don't have an acid, so B is not showing effervescence. C is also not showing effervescence because no acidic group in it. And D is having a carboxylic acid group. So it will also show effervescence. So now we have to decide between A and D. Now, last one, they are saying hot potassium dichromate acidic remains orange. It means no reaction, right? Okay. Here in option A, we have alcoholic group. So this alcoholic group can undergo oxidation. And if it undergoes oxidation, it will give us ketone because it's a secondary alcohol. So the color of this potassium dichromate that will change from orange to green. But they are saying remains changed. So it's not option A. Now here in option D, we have again alcoholic group, but here the alcohol is tertiary alcohol. So we know that tertiary alcohols do not undergo oxidation reaction by the oxidizing agents. So they do not undergo oxidation, the tertiary alcohols. So that's why the color of this uh, potassium dichromate that will remain orange. So that's why option D is correct for all these three. So X is this compound. Clear?